Without further ado, I turn it over to Corey Kallenberg and Zeno Kova for their demonstration.
Okay, thank you. So yes, I'm Corey Kallenberg. Audio okay? Everyone can hear me? Good? Okay, next to me I have Zeno Kova, my colleague, and today we'll be talking about extreme privilege escalation on Windows 8 UEFI systems. And you're probably asking yourselves, what qualifies as extreme? Well, you will find out in this presentation. So who we work for the MITRE Corporation, which is essentially a company that manages several federally funded research and development centers. Our primary customer is the U.S. government. You've probably heard of us through things like CVE and things of that nature, but we're part of a team that's done a lot of BIOS research in the past year or two, so maybe you've heard of us through that. All right, outline for what you'll be exposed to today. The agony of Ring 3. Yes, we can get to administrator Ring 3 command prompts in Windows 8, but there are further places we can go, more extreme lands, better things we can do, and we're going to talk about what that is and where we can go and so forth and so on. We'll talk about why we would want to go beyond just privileged Ring 3. We'll be talking about some exploits that we found in UEFI, which is running underneath the operating system that allowed us to go to these strange new extreme places. What will warrant discussion as well, which is pretty interesting, is that these vulnerabilities we found in UEFI that we exploited, the BIOS ecosystem wasn't really well prepared to deal with BIOS vulnerabilities at the time because there hadn't been a lot of BIOS vulnerabilities, period. So what happened and what unfolded due to our disclosure kind of warrants discussion, and we'll talk about that as well. We'll talk about what we can establish in these other privileged domains like system management mode and in the firmware, which can do good things from an attacker's perspective. And then finally, we'll introduce, or not introduce, but sort of re-emphasize a free tool we have out there that can check if you've been attacked at this firmware level. It can go and read your firmware and see if anyone's been trying to attack you at this level. Okay, so yes, we are administrator, Windows 8 command prompt. Most researchers at this point would type calc.exe, it would pop up and they'd say, okay, great, I won, I'm the winner, collect your bug bounty, that's it, game over. But what you don't see is you are still bonded by chains because you are in Ring 3. There are places you cannot go, memory you cannot read, instructions you cannot execute. These are the things we want to pursue. As attackers, obviously, we always want more persistence, more power, more stealth, and there are limits to these things in Ring 3, even as an administrator, so we have to go beyond Ring 3 into the unknown, into these extreme lands that we're going to talk about. Now, at this point, I'm sort of done with my introduction, and some of you are probably wondering, do I want to stay for this talk? Is it going to be interesting? Is it going to be boring? Maybe I should have gone to the Bitcoin talk, but I will tell you, you definitely want to stay because this talk is going to be 11 out of 10. Awesome, would buy again. You don't even have to trust me. You can trust the authority figure on this subject, Snare himself, because in this slide from one of his presentations, he said, if we can reflash the firmware, that would be 11 out of 10. A++ would buy again. Super awesome. That's great. And that's exactly what we're going to do in this talk. We're going to reflash the firmware despite signed BIOS enforcement by exploiting a generic UEFI vulnerability from a Ring 3 Windows 8 process. So this general attack model that I personally like to explore is what I refer to as a post-exploitation privilege escalation. So once you're, most people would consider once you have the administrator command prompt, the exploitation phase is over, but there are other places you can go that require exploits to get to. And the most common one that has been explored by other researchers is escalation into Ring 0. So even from an administrator account on Windows 8 or on later versions of Windows, you can't just arbitrarily get into the kernel. You can't get into Ring 0. And this is due to the signed signed driver requirement. It won't just load any driver into the kernel. It has to be signed with an authenticate certificate. Now, there are things you can do, and this attack model has been explored. Juru has an excellent series of articles about how you can get into Ring 0 from administrator Ring 3. Joanna Rutkowska, back in the Windows Vista days, talked about how you can load a known vulnerable but signed driver and just exploit that to get into the kernel. So, yes, this is probably the most typical post-exploitation privilege escalation, and we don't want to talk about typical, we want to talk about extreme, because that's in the title of this presentation. So let's proceed. Now, we do have some other options for what we can do, where we can go after we have finished the exploitation phase and after we have administrator command prompt. So one thing you often see is that you can bootkit the system, or you can make a BIOS rootkit, or just jump into system management mode and so forth and so on. And in recent history, maybe 5-10 years ago, all of these options were completely possible. Nothing stopped you from doing this. Unfortunately, we live in a dark world now, from an attacker's perspective anyway, and we can't explore these new lands, we can't go to these new places because there are barriers in place. For instance, For administrator ring 3, we can't bootkit the system because of secure boot. Secure boot will sort of prevent you from doing that. You can't get into the platform firmware because of signed BIOS requirement. All of your rights to the BIOS have to be signed. And you can't get into system management mode because the memory controller hub is just going to block you from doing that. Non-SMM accesses are not permitted access to SMM memory. You cannot even read SMM from ring 0 code. So it's a dark place we live in today. Lucky you are here at this talk. And we have extreme privilege escalation, which is exactly escalation from privileged ring 3. You do have to be administrator all the way to the platform firmware using only a special Windows 8 API. And what's nice about this is on this diagram, it's essentially organized as what's lower on the chart is less privileged and what's higher is more privileged. So the privileged domains highest on the chart is the firmware, because that is responsible for configuring the platform. It is the very first code to run, so it's really the most powerful code that can execute on the CPU. And anything higher on this list can essentially compromise things lower on this list. So if we could get into the platform firmware, then it's totally possible for us to just snake our way down, corrupt the operating system, get into system management mode, bypass secure boot and so forth and so on, and we could like corrupt a hypervisor in there too if I had that, included that in the diagram. All right, so our target of attack. Pretty much every new Windows 8 system you'll go out and buy today has UEFI firmware running underneath the operating system. UEFI is sort of the replacement for conventional BIOS. It's kind of become popular in the past few years because Windows 8 has basically required that you have to have UEFI to get the Windows 8 sticker, so that's really caused a large migration from legacy BIOS to Windows 8. Now, this is the obligatory UEFI diagram that every low-level researcher is going to put in their presentation. The main responsibility of the UEFI firmware, or firmware in general, is to configure the platform, find the operating system, and then transfer control to the operating system. And what you have here is time goes, starts on the left and goes to the right. So left on the diagram is earlier. And the most important thing to take away from this slide is that it's always advantageous really to execute earlier on the platform. More early, more power, because on the left, the platform is less locked down. Essentially what the BIOS does is as the boot up of the platform continues, more and more locks are applied, more things are configured. There are less things you can do because the BIOS is going to set locks that can't be unset until the next reset of the system. So it's advantageous as an attacker for us to be as left as possible on this diagram. Now, with Windows 8, they've introduced this new API called set firmware environment variable, which allows the operating system to interact with these UEFI configuration variables that are stored on the flash chip. Now, these variables do a number of things. They're usually responsible for things like the boot order, the platform language. They also have a lot of weird proprietary uses like things with S3 sleep and so forth and so on. They're used for all kinds of crazy things. Basically, just think of them as like environment variables in Unix. So with that analogy in mind, my main responsibility on the BIOS team is sort of vulnerability research and exploitation. And since we wanted to look at UEFI from an attacker's perspective, I thought, okay, how am I going to go about attacking this thing? Well, I know that from the Windows 8 command prompt or from Windows 8 administrator, I can get access to these UEFI environment variables that it's going to use and parse and so forth and so on. And that got me thinking back to the old 2000s days where we had lots of these Unix-style privilege escalation vulnerabilities where you would do something like set term equals A times a million. Then you would run some, privileged application and it would parse the variable in question and you could escalate from non-root to root. Everyone remembers this type of attack, right? It was very popular back then and it was definitely at the forefront of my mind when I started attacking UEFI. I thought, okay, I can control these variables, so let's definitely look at it from that perspective. Many of these variables have like pretty complex contents. They're like over 1,000 bytes in size. They're completely proprietary. They obviously have pointers, integers, things that you typically find in memory corruption, vulnerability type parsing things. So one of the most important takeaways from this presentation that I want everyone to get is that this UEFI variable interface is essentially a conduit by which a less privileged domain, admin ring 3, can transmit data for a more privileged domain, the platform firmware, to consume. So this is the attack surface where you usually want to explore. You want to go from less privileged to more privileged. Or here's your interface right here. Now, we've already looked a little bit at this interface. Earlier this year, we co-discovered a vulnerability that allowed the bypassing of secure boot, and it had to do with essentially a IBV, independent BIOS vendor, OEM implementation mistake with the way they were using one variable that allowed people to bypass secure boot, which prevents bootkits, of course. But maybe this vulnerability was only like a 5 out of 10 on the awesomeness, snare awesomeness scale, because it only let you bypass secure boot. You could use it in weird ways to break the system as well, but it wasn't present on all UEFI systems. It was only on a subset of systems, basically OEMs or IBVs that had done something a little bit wrong. So we thought, okay, we're not satisfied at 5 out of 10. We definitely want 10 out of 10 or 11 out of 10 on the snare awesomeness scale. So we are going to go straight for the gold and try to find a generic UEFI vulnerability that lets us reflash the firmware. Now, in order to do this, it's important to talk about the BIOS or the firmware development ecosystem. And this is sort of an idealized view of how it works, but it sort of serves the purposes just to illustrate how this generally works. So at the top of the pyramid, we have the UEFI reference implementation, which is some open source code that Intel provides that is just like a skeleton for this is how UEFI is supposed to be programmed and so forth. Now, one step lower on the pyramid, you have the independent BIOS vendors. Like you've probably heard the term Phoenix, American Megatrends, Inside, etc. And theoretically, those IBVs will take the UEFI reference implementation, use it to develop their own firmware development kit, and then they will sell that firmware development kit to OEMs like Dell and HP and Asus, etc., who will then use the IBV development kits to make the BIOS or the UEFI firmware for the models they actually go out there and sell. So this is idealized. We'll talk a little bit more about how it's actually crazier in this in the long run. But the point is, if we could find a vulnerability in the UEFI reference implementation that Intel provides, it would proliferate down to all these other entities, and we would have a widespread vulnerability that affected all these other people like American Megatrends, HP, etc. Now, what's nice is auditing UEFI with this sort of attack methodology is quite easy because it's open source. You can go and just SVN check out UEFI and then go to work on trying to find vulnerabilities or whatever. And anyone in here that's a veteran source code auditor will know, well, where's the first place you start? Obviously, you want to identify what is attacker-controlled data, where does the more privileged domain, the firmware, consume data from the less privileged domain, basically anything that's not the firmware. And as I've already mentioned to you, one very obvious domain is the UEFI variables. We know that these could be controlled by the operating system and that many of them would be consumed by the UEFI firmware. So this was definitely an attack surface where a more privileged entity, the firmware, was consuming data from the less privileged entity, the operating system. Now, last year we presented an exploit against the Dell BIOS update process, which essentially allowed us to bypass the signed BIOS requirement on a number of Dell models by finding a memory corruption vulnerability in the Dell BIOS update routine. And so we had some experience with attacking BIOS update routines. And so with that in mind, when we were looking at the UEFI specification, there's a generic way to update your firmware in UEFI called capsule update. And it's not directly callable by Ring 3 code. You can't just call the capsule update process even from administrator in there. But it can inadvertently be started by the creation of a special UEFI variable. Essentially, creating a specific UEFI variable would inadvertently start the capsule update process. So this was interesting because it was a nice intersection between things we had experience with, firmware updates, and things that we were interested in, UEFI variables. So we said, okay, capsule update is a great target. Let's go about trying to exploit UEFI via its capsule update interface. All right, so just to, before we start how we're attacking it, just a general description of how it works. You have this firmware capsule on the left, which will do something like update your firmware. That's kind of what it looks like. There's a number of envelopes encapsulating the capsule. The operating system does something interesting with these capsules in that it scatter writes the capsule to the address space. And that's because the capsule might be pretty large and the resources might be constrained on the OS. So you might not have a large physically contiguous gap in your address space. So the OS can fragment the capsule update and just put it all over the address space. Now, what actually kicks off this capsule update process is the existence of this capsule update data variable. So this is essentially a pointer to a scatter-gather list. And when the platform reboots, UEFI will check if this capsule update data variable exists. And if it does, it'll automatically initiate the capsule update process. and try to parse the scatter-gather list and coalesce the capsule. So yeah, coalescing looks something like this. UEFI parses the list, it goes and he finds all the fragments, and then at the end you end up with the complete reconstituted capsule image that you originally started with. And then once you have that reconstructed image, UEFI is going to parse the envelopes of the capsule. It's going to verify that its contents have been cryptographically signed. It shouldn't be the case that you can just throw unsigned capsules at the firmware and the firmware will process them. That would be just like a design flaw, because all of your updates to the flash have to be signed. So yeah, there is some verification going on here that the capsule is signed by the OEM. But what's interesting is that the individual fragments are unsigned, and there are a number of these envelopes that are parsed before the cryptographic verification occurs. So there is a attack surface you can hit. So yeah, after everything's been cryptographically verified, it's going to run the contents of the capsule, and this is actually more of a generic capability. It's not necessarily just for firmware updates. I've seen proposals as well for using this for like running malware independent of the operating system. But yeah, I think the main idea was to use it to securely update the firmware on your system. So with all that in mind, how this generally works, we identified 3 places we could potentially go after the UEFI capsule update process. One, we could go after the coalescing phase, because that definitely occurs before any signature check occurs. For you guys in the back too, there's plenty of room on the right, just so you know. Monitors over there. I want everyone to be able to see. So yeah, coalescing phase, that's definitely attack surface. Parsing of the capsule envelopes. As I mentioned before, there were several envelopes that have to be parsed before the cryptographic verification can occur. Any memory corruption vulnerabilities in there could potentially be used to hijack control of the instruction pointer in the context of UEFI. And then the third option was potentially parsing unsigned content embedded within the capsule or the firmware update. And what's interesting is this last option was actually where the first exploit against the BIOS was presented. In 2009, Invisible Things Labs presented an attack against Intel BIOS, where they found that you could embed a special splash screen into a signed Intel BIOS update. And that was to like customize your boot up splash screen if you wanted to put your organization's logo on there. And they found that there was basically a memory corruption vulnerability in the parsing of the splash screen, and that allowed them to reflash the BIOS with an arbitrary image despite the presence of this signed BIOS requirement on the Intel BIOS. So that was the first one. That's interesting. We actually chose to go after the first 2, really. And yeah, we found bugs and wrote exploits for both of those phases. So yeah, I don't want to bore people with the details, but we spent about a week auditing the open source reference implementation, and we found a lot of bugs. A lot of them, what's interesting, is took the form of like integer overflow 101, don't do this. Any veteran source code auditor would have spotted these very quickly. So yeah, we found bugs both in the coalescing phase and in the envelope parsing phase. For UEFI people in here, or people that might know about UEFI, the coalescing was in the PEI phase, and the envelope parsing was in the Dixie phase. And we called, well, first of all, Zeno and I are big nerds, obviously, because we do BIOS stuff. You got to be a nerd to like BIOS stuff. And by way of being nerds, we also like chess a lot, so we started calling all of our attacks after like chess openings. So we called the envelope parsing one the King's Gambit, and the Queen's Gambit one is the coalescing vulnerability. So when I refer to those in later slides, that is what I'm talking about. Queen's Gambit is the exploit in the vulnerabilities in the coalescing phase, and King's Gambit is in the envelope parsing and what's known as the Dixie phase. So what's interesting is all these vulnerabilities, they occur very early in the platform. So remember I said the earlier you can execute, the better. Well, it turns out that both of these vulnerabilities, the code occurs very early in the boot up process when the platform is still relatively unlocked. So if you can leverage them to get control of the instruction pointer, the platform is still in an unlocked state where you can do really crazy things. Now, just to reemphasize, what's interesting is that this UEFI code, this reference implementation, is completely open source, so it's very easy to audit. And it's obviously security critical. This is the code that is responsible for making sure that our firmware can't be corrupted, we can't get BIOS rootkits, so forth and so on. But these vulnerabilities were very easy to find, so we're forced to conclude that not many people are actually looking in this space. Is anyone else actually auditing the UEFI code? Obviously not, because other people would have found these vulnerabilities. And the other funny thing is, in the UEFI code, I found like lots of little comments that said like, well, you can see here, more reliabilities, checkup we'll do later, and things like should add sanity checks here. Things where clearly the developers know that there could be issues, could be vulnerabilities, but yeah, the vulnerabilities were just waiting there waiting there to be fixed. And since they were in the reference implementation, they proliferated down to other entities like OEMs and IBVs that were pulling code from the reference implementation. So more people need to be looking there. For other vulnerability researchers in the audience, go and look at the UEFI code. Now, the vulnerabilities were easy to find. They took the form of integer overflow 101. Don't do this. Don't do math and arithmetic right before you do an allocation, and so forth and so on. That's always a red flag when you're looking at code. Like, just to go back, yeah, you can see like memory size less than arithmetic. That's definitely not good. Multiplication before allocation, definitely don't do that. If you're a bug hunter, you'll definitely zero in on that and be like, that could definitely be problematic. So, yeah, pretty easy to spot. Now, what's good from an attacker's perspective, too, is the bugs are easy to spot, and actually this code runs in an environment that is read, write, execute for the most part. It's a flat protected mode with paging disabled, and since memory protections are typically applied at the paging level, things like your no execute stack and so forth, since paging is disabled, these mitigations don't exist. In fact, there's really no mitigations in this space at all. For the most part, things are at predictable addresses, and yeah, so from an attacker's perspective, this is like the 90s when you're trying to go after bugs and there's no mitigations. However, despite all these things that are good for an attacker, it turned out that exploiting these bugs was actually very complex because of the strange environment we were working in and so forth and so on. So yeah, it took us a week to look at all these bugs, but just to give you an idea of the timeline, it took me probably a month to develop each exploit. So both the King's Gambit and the Queen's Gambit took me about a month each to exploit, even though it only took me a week to find the bugs. Now, previously, when I've come up here and given presentations, I've gone line by line through IDA assembly, and this is the memory map, and then I moved this here, and this is the return-oriented programming payload. And after 10 minutes of that, the audience was totally asleep, so I'm not going to do that to you guys because probably the majority of you would totally hate that, and it would not be entertaining. So instead, I'm going to show you this cryptic diagram. And other vulnerabilities researchers in the audience, I hope this will entice you to go and read the white paper. I made the white paper very detail-oriented. It's 20 pages. It'll totally put you to sleep with details. But if you want to know the details of how we exploited these, please, please, please go read the white paper because I put a ton of effort into it. And yeah, the exploitation process was pretty interesting. But this right here is the Queen's Gambit. This is in the PEI coalescing phase. And yeah, crazy multi-stage stuff going on. But at the end of the day, what's interesting and noteworthy about this is we ended up with a very reliable surgical write what where primitive. So if you can get write what where when you're developing an exploit, that's pretty much the holy grail. And once you have that sort of primitive, then everything else falls down. So yep, that's good for PEI coalescing. Now this was the Dixie phase vulnerability and how I exploited it. This one was especially crazy. Please go read the white paper. So what was interesting about the Dixie vulnerability, the envelope parsing vulnerability, was I would essentially end up, when I caused the memory corruption, I ended up in a non-terminating loop that would overwrite the whole 4 GB address space with only semi-controlled values. So how can I possibly escape this non-terminating loop of doom? Well, with paging disabled and so forth, basically the only thing that I could think of to do was to overwrite the non-terminating loop itself. So have the non-terminating loop that's overwriting everything actually overwrite its own code, overwrite its own loop code. And you can see here in the diagram, I have the basic block. It's maybe hard to read, and that's the loop that's just totally clobbering the address space. And as I mentioned, the values that were being written were only semi-controlled, so I had to write a crazy Python brute force script that would just brute force all the ways I could set this up and what that would end up overriding the non-terminating loop with. And eventually, it came up with a way I could set things up where it would overwrite the top of the non-terminating loop basic block with a jump away instruction that would jump to a part of the address space that hadn't been corrupted and was controllable by the operating system. So this would let us get control of the instruction pointer in the context of the UEFI firmware with arbitrary operating system shellcode. But it's not quite as reliable as the other vulnerability that I just showed you. It corrupts a lot of the address space, so it destabilizes the system, but still it was kind of entertaining to try to exploit. So read the white paper. All right, so the summary here was that, like I just said, read the white paper for the super nitty-gritty details. I don't want to put people to sleep with the whole memory map and this and that and so on. But yeah, capsule coalescing exploit was very reliable. We could exploit it using only that special Windows 8 EFI variable API. And part of the thing we had to overcome was how do we stage things at reliable physical addresses from Ring 3 userland. Well, it turns out that we could further abuse the Windows 8 UEFI variable interface and just create a whole bunch of EFI variables. And the contents of these EFI variables were actually written to the flash chip, and the contents of the flash chip were mapped to physical memory. So by abusing this interface and doing what's like a heap spray in the UEFI world, so like variable spray, we could end up with operating system Ring 3 controlled contents at predictable physical addresses. Now, so yeah, that's all good. That was the coalescing one. The capsule envelope vulnerability and exploit destabilized the system. We could control the instruction pointer and reflash the firmware, but the system was unstabilized, and we did have to rely on a crutch, a third-party driver to stage things at certain physical addresses. We couldn't find a way to do that with just the EFI variable API. So not quite as good, maybe just like 9 out of 10 on the snare scale, but definitely the first one is 11 out of 10 on the snare awesomeness scale. Okay, how's everyone doing? Totally boring? What's going on? What's Corey talking about? I have no idea. Well, it's like, yeah, I know it's kind of hard to conceptualize these types of attacks because it's a lot of people haven't done these sort of things. It's sort of a new kind of attack, going after the firmware and these capsules and so forth and so on. So let me help illustrate what is going on. Well, we have our Dark Jedi, Sith Lord, who is not satisfied with the constraints of Ring 3 Administrator. He must grow his power. He must learn more, get more power. He must explore new dimensions. So he's unimpressed. Great. Administrator command prompt. Let's go elsewhere. Well, first thing he does is he creates a bunch of these EFI variables using this special set firmware and variable interface. He sprays the flash chip using this variable spray technique. And after he has just created variable, he knows that beyond a shadow of a doubt, at address FFF91000, he will have attacker-controlled contents there, which essentially breaks down to shellcode and an evil scatter-gather list that will get control of the instruction pointer. So just like heap spray, but in the UEFI context, using this variable interface. Next, our Dark Jedi creates the capsule update data variable, which is automatically parsed by UEFI upon reset, and he points it at the payload that he just sprayed all over the flash chip. Next, a platform reset occurs. So I'm going to have to wave my hands a little bit because this is actually implementation specific. In most cases, this means S3 sleep, but it could be different. If you look at the UEFI reference implementation, the platform reset, a warm reset, will essentially turn into like an S3 sleep with immediate wake, but it could be different. And I'm going to have to, when we actually demo some of these attacks, talk about what is actually going on and what we're having to do. But from an administrator command prompt, you can cause this to occur by messing with powerconfig.dll. There are special parameters you can pass it, and it will put the system into the needed state to initiate this capsule process if you have created that special capsule update data variable. Okay, so the platform reset occurs. Now UEFI has gained control again. EIP is pointing at UEFI code, and it's doing its thing. It very early checks, does capsule update data exist? If it does, it automatically tries to parse that scatter-gather list, and our Dark Jedi has placed the evil payload there, and it will be consumed, and bad things will happen. So, yep, UEFI will begin to coalesce the evil capsule that will cause the vulnerability to occur and will allow us to get control of the instruction pointer. And then at this point, the UEFI code will become corrupted. And what's nice is the attacker can now deflect the instruction pointer to the contents of his shellcode, which is stored in one of those sprayed variables. And at this point, the platform is completely unlocked. So remember I was saying that on modern systems, by the time you get to the OS, the platform is very locked down. There's a lot of things you can't do. Well, in this part, in PEI, very early in the boot up, the platform is completely unlocked. You can pretty much go anywhere, do anything that the CPU can possibly do. You can copy yourself into system management mode. You can reflash the firmware. I mean, anything the CPU can do, you can pretty much do at this point if you really want to. Now, once the attackers establish themselves in system management mode, once they've escalated themselves from admin Ring 3 all the way to system management mode of the platform firmware, there's a lot of different things they can do. This is just sort of a summary of results that other people have presented. They can brick the platform, obviously, by just writing 0 to the firmware. They can defeat secure boot because the secure boot code is stored on the flash chip as well. UEFI implements secure boot, so if you can change UEFI, obviously you can defeat secure boot. You can have an undetectable SMM rootkit. You don't believe me, but you totally can. We have presented work last year At Black Hat, we presented a BIOS chronomancy work about undetectable BIOS rootkits. We also talked about undetectable SMM rootkits at CanSec West this previous year. So yeah, you can do all kinds of crazy things. I encourage you to check out those slides if you don't believe me. You can subvert hypervisors because according to the negative ring scale, hypervisors are ring -1 and system management mode is ring -2. So if you can get into SMM, which you can with this attack, you can subvert hypervisors. You can also, on most systems, subvert TXT late-launched hypervisors. So no, not even TXT can save you here because SMM transfer monitors basically do not exist. And without SMM transfer monitors, you are totally doomed if there's a BIOS-level attacker. And yeah, there's all kinds of other crazy things you can do. Once you're in the BIOS and SMM, the world is your oyster. Now we're going to start. So I want to say before we begin, actually, normally Zeno and I just use like videos because videos are safe. Maybe some people complained about that. So you see all this crazy stuff up here. We are going to attempt a live demo of UEFI exploitation from Ring 3, and installing an agent to the BIOS is going to be totally crazy. Don't know if it's going to work, maybe 50-50. So everyone pray to Papa Legba, the god of Haitian voodoo, that yes, please, Papa Legba, hear my call, make our demo work. Okay. Oh yeah. So I forgot. Go ahead and run the exploit, Zeno. Very easy. All right. So what just happened is you can see the creation of all these UEFI variables, like variable spray 0, variable spray 1. This is just filling up the contents of the flash chip with our shellcode, with our evil scatter gather list, so that we can get things at a predictable physical address after a while. You can see it says error after a while. Zeno, basically it said error just because it had run out of. The variable range had been exceeded. There was no more space it could possibly consume. So then it said, I can't create any more. Your spray is over. And it also seeded that evil capsule update data variable into the variable space. Okay. One thing I'm going to have to wave my hands on a little bit here. You would be able to instantiate the vulnerability just from the command line on an enterprise system by using power config and stuff like that. We're actually having to do something a little bit different on these minnow boards. You can see them up on stage with these little development systems. And the reason is there basically aren't drivers for the minnow board, this development system we're using to run Windows 8 on. They're not really even supposed to use Windows 8. We just liked them because they had JTAG support and they're small and easy to move around. But the point is, since there weren't drivers for them, Windows 8 doesn't really know how to put the system into S3 sleep. So we're actually having to boot to the EFI shell to then do a warm reset, which will put it into S3 sleep. So normally we could totally do this just from the administrator command prompt. Please believe me, I know I'm waving my hands, but we're having to actually initiate the warm reset from the command prompt. Did we get the right address? Good. 40C2? Yeah. So yeah, we are just basically seeing if our demo is going to work. We see that FFF940C2, that's an address that we've determined we can reliably put stuff at. Since I see that address, I'm feeling pretty confident the demo is going to work, but we'll see. And yeah, we just did reset W, and what this does is it puts the platform into S3 sleep with immediate wake, and we couldn't do that from Windows 8 because we didn't have drivers for the minnow board. We didn't have Windows 8 drivers for the minnow board, so we had to use the EFI shell. So normally this could all just be done seamlessly from the Windows administrator command prompt, but we are having to do this little crazy shim thing here. So it's still cool, I promise. Okay. Okay. So one interesting thing is happening here. When you put the minnow board into this warm reset, sometimes it takes a while to restart. Like sometimes it's immediate and sometimes it takes like a minute. So we're going to wait a second, and hopefully eventually you'll see like running from SPY Flash, which means that it is booting off the firmware, and then we'll get to the point where actually instantiating the vulnerabilities and corrupting UEFI. So let's see, let's cross our fingers. Okay, while we're waiting, does anyone have any questions?
So I understand why you use these boards for development because the JTAG is.
Yeah.
Repeat the question.
So his question was, why wouldn't we transfer the exploit to a normal Windows machine? We actually did that in the white paper. So if you want to know the details of how all we did that in the white paper, then yeah, you can look at that. So why are we not exploiting that on stage today, I guess is the question, is because the exploit was basically just proof of concept, and we just corrupt the address space and stuff on the real enterprise system. And because we didn't have JTAG access, we didn't go so far as to weaponize the exploit on the enterprise system. But the system we actually exploit in the white paper was an HP Elite book, and we actually have a representative from HP coming on stage later today to talk about their response to this issue. So in terms of exploiting real enterprise systems, all those details are in the white paper. Does that sufficiently answer the question? Yeah. Did it go? Okay. Zeno just going to manually try to reset again, since sometimes it just doesn't want to reset. Yeah, so it's still there. Yeah, we'll see. There we go. So this time it worked. I don't know why. So at this point, the firmware is consuming that evil capsule, and at this point we've probably gained control of the instruction pointer, and it's using our shellcode, which is making writes to the SPI flash on the system, which normally you absolutely cannot do. Normally by the time the operating system gets control, you can't make writes, arbitrary writes to the SPI flash. But since we got control with our shellcode very early in the system, we're able to arbitrarily modify the contents of the platform firmware. So yeah, what Zeno has here is actually he's connected an EEPROM programmer to the Minnow board. Another reason we like to use this is it has really easy EEPROM access. So we can just show that, yes, we have actually made changes to the SPI flash chip.
Screen resolution's too small again. No, we'll call it good.
What were the, is that just the variables or whatever?
AV people, do you care if we reset the screen resolution? Is that going to throw everything off? Can I get a thumbs up or thumbs down? Is that going to mess it up? Not you, AV people. All right, well, they're not saying anything, so we're going to try it anyways, just to show like the actual payload installed. We're just going to change the resolution because this tool is not great at other resolutions. It's Windows too small.
Yeah,
Okay, yeah, you good. All right, so just wanted to show like concretely, exactly where we put it. 3FEDE0. Right, so this is the actual exploit payload. So originally it was a bunch of Fs. Right, we just picked a place in the flash chip where there's a bunch of Fs. We said, okay, we're going to stage our attacker code there. This is basically the backdoor which is being installed. We'll talk about that a little later. But this means the exploit has actually run. It has gained control. It has then run code which knows how to flash stuff to the SPI flash chip. And now we have an attacker backdoor just sitting around in flash chip waiting to be executed on next boot of the system. It's going to be invisible. We'll talk about it a little later. Anything else?
I think that's it.
All right, so we're going to talk a little bit about the vulnerability disclosure process before we come back to that. So, right, this shows that our exploit actually worked. We were able to reflash arbitrary contents into this flash chip, let it live forever. And so, yeah, basically, we already alluded to this fact. When we found these vulnerabilities, we're doing defensive security research. We're looking at the source code. We're trying to find vulnerabilities because we know that, like, architecturally, if attacker gets in at these earliest phases, then they control the system, they own the system, and we don't want other people doing that. So we want to squash bugs, find vulnerabilities, and let people know about it. Yeah, can you do Linux? So we told Intel about these problems because Intel sort of maintains the open source reference implementation. We told them about the problems back in November, December. And we said that we would do our typical thing with sort of 6-month vulnerability disclosure. So when we find vulnerabilities, we tell the vendors about it, and then we say, okay, 6 months from now, we'll make these public. Because if we don't have some 6-month or whatever deadline, then BIOS engineers are busy. They got a whole lot of other stuff that they got to do, and maybe these vulnerabilities are not going to make it to the top of their priority list. So we use that to help incentivize things. People who don't have deadlines don't get stuff done. So Intel turned around and fixed the bugs relatively quickly. In January of the following year, they fixed the open source reference implementation, and then most recently, in March, they rolled a new sort of UEFI stable version, the UDK UEFI Developers Kit. And that's sort of the stable build of UEFI where they just slap it, snapshot it, and say, okay, BIOS vendors, start building new BIOSes from this, right? So that's patched in that, and then Intel, we sort of asked Intel to do coordination to tell all the various IBVs, independent BIOS vendors, and OEMs about these vulnerabilities to find out like who's affected, which systems are affected, and so forth. And so Intel went and had meetings with the BIOS vendors, told them about it, and answered their questions and so forth. But when they went to say, okay, well, so dear BIOS vendors, dear OEMs, which systems are actually vulnerable, which contained the exploitable vulnerability, and when are they going to be patched, and where are you going to put the patch information, Intel didn't really hear anything back from a lot of people on that. And similarly, then we didn't hear anything, and around June, we started to get a little nervous. We said, look, we told you up front it's going to be public, in the Black Hat time frame. So where are we standing? Like, who's fixing things? Where are the patch lists and stuff like that? And so what we basically got was a taste of the bad old days where people just don't reply, people don't indicate which things are actually patched. Some information was shared with Intel under NDA, and so we don't know that either. And so, yeah, basically then we had to, when we found out that this information wasn't getting back to us so that we could give you information about which BIOSes you need to patch, which things are vulnerable. It wasn't getting back to us, so we did like sort of an aggressive last-minute follow-up, and we'll share the results of that here in a second. But basically the point is BIOS vendors not really used to having to deal with vulnerability disclosure. They're a decade and a half behind the OS vendors who've been getting hammered on this for quite a while. All right, so this is our basic current understanding. Intel obviously patched it a while back. Phoenix, Insight, and AMI, they're all independent BIOS vendors. They were either vulnerable and fixed it, or they believe that they're non-vulnerable. We have their official responses on the next slide. HP, as was mentioned, we just had an HP system sitting around. We investigated. We said, okay, did the vulnerable reference implementation code actually make its way into a real shipping BIOS? And we found that it did, and then the white paper describes how we exactly identified it and proved it. So HP was vulnerable. They've fixed things. We'll bring a HP representative up here in a second to talk a little bit about what they did, how they coordinated, how you can disclose vulnerabilities to them in the future. Dell, we did an investigation. We found that their code was in the BIOSes, but the current evidence is that it's not actually being invoked, so it's just dead code off to the side, and they're going to remove that in the future. And so unofficially, Lenovo didn't give us an official statement, but unofficially they're coordinating with their independent BIOS vendor, as is Panasonic. And other vendors, we don't know because we've been trying to get contact information for those vendors, and we haven't been given it. So Phoenix, AMI, and Inside, you can read this later, but that's their responses, with 2 out of 3 saying they're vulnerable but fixed, and 1 of them saying we didn't include that code. So how coordination can be done sort of in the future better? I think that CERT is Computer Emergency Response Team or Readiness Team or whatever. They're a neutral, independent organization. Their whole job is just doing coordinations on vulnerabilities and that kind of thing. And so originally we asked Intel to coordinate the vulnerability because obviously they work with BIOS vendors very closely, and consequently they have a lot of BIOS vendor contacts. And so the problem with Intel doing it is that at the end of the day, BIOS vendors are they're customers of Intel, right? So they buy chips from Intel, and Intel can recommend things, but Intel can't tell them to do things. And there's certainly plenty of guidance out there that Intel gives them that they aren't necessarily following. So the one ray of hope here is that the UEFI forum has moved away from being just a standard specification type organization and actually being proactive now and setting up a security response team. It's set to go live on September 1st, and they will handle the sort of coordination within the UEFI ecosystem. So we already talked about how these source code level vulnerabilities sort of trickled down and made their way into real systems. MITRE, we're independent organization, we're not commercial organization, we're sort of neutral in here. We just attacked an HP system because we had an HP system laying around. Just like last year we attacked a Dell system because we had a Dell system laying around. So we wanted to, just like last year, we wanted to have we wanted to have an HP rep come up, give some contact information, talk a little bit about what they're doing in BIOS security, and then after he's done, then we'll go on to talk about what does the backdoor actually do now that we've installed it. So Jim, if you could come up. That's live.
Thanks for the opportunity to speak. I apologize up front. I've been battling a horrible cold all week, and so far I'm not winning. So I will do my best to power through this. My name is Jim Waldron. I'm a senior technologist for the division of HP that builds and sells business-focused computers. That's desktops, notebooks, and tablets. First off, I want to say that HP wants to acknowledge the very real value provided by MITRE and the important role they play in securing the devices that we all depend upon each day to do our work. Their information and disclosures on vulnerabilities allow us to do mitigations that otherwise might be exploited by, bad people to do bad things. And some of you know who you are. In addition, however, MITRE is not the only research facility out there, and we encourage anybody who discovers any security issues with our stuff to let us know. We take all security information very seriously. If you wish to report a security issue to HP, please contact our software security response team. You can reach them at security-alert@hp.com. As far as this specific vulnerability and its use on an HP 2540p EliteBook, just to put it in context, the EliteBook 2540p first shipped in March of 2010. To give you an idea of what that kind of means in computer years, it's very likely that the designers who put this system together had never heard of Windows 8 at that time. That said, this is a real vulnerability, and we have provided a fix. So there is a location where you can get an updated BIOS that contains the resolution of the issues discussed by MITRE in this briefing. And you can get it at the support, drivers, and downloads page for the 2540p at hp.com. If you have additional questions about this vulnerability, I'm not going to answer a bunch of questions here. These guys need to get on with their demo. But we do have a HP security bulletin available, and we've provided a link here where you can download that PDF and get additional information. Now, we all know that there's no actual magic bullet to get rid of all vulnerabilities in a system. It's particularly challenging for BIOS engineers who have a hard time anticipating the tools and techniques that might be used by attackers as many as 4 or 5 years into the future when they design their systems. That said, HP believes that security of the BIOS is a very important area, and we're putting a lot of research and effort into technologies to help in this area. We started rolling out a new technology called SureStart in 2013 to our elite level of computers. The SureStart system leverages an additional separate root of trust for measurement that can independently measure the BIOS and ensure that it hasn't been modified. When it detects a modification, it can also restore that BIOS to a known good, safe state. And it can do this all automatically. Depending on the security policy settings and the configuration, it's possible for it to completely restore the system before the first line of BIOS code ever runs and without any interaction by a user or an administrator. So we believe that SureStart and other similar technologies will be a more and more important part of security in the PC ecosystem going forward. So I appreciate your attention, and I'll give it back to the MITRE guys who have more cool demos to show you.
All right, thanks, Jim. So yeah, we just wanted to give a hint that, there are increasing BIOS security techniques coming down the line, and people need to sort of be aware of them and what they can do. So, all right, we're going to just power through this, right? We already had, this is good because this told me, who the tourists are and who the people are that actually care. So, we have a little proof of concept here. So the exploit, the Queen's Gambit exploit, which we ran, installed a backdoor into the BIOS. This backdoor is going to run at every system boot. It's going to install itself into system management mode. We call this proof of concept the Watcher. If I had more time, I would tell you all the comic book analogy, relevance, and so forth. But the key point is the Watcher lives in system management mode, which is the location where it can see everyone's memory, but no one can see its memory. So you can never directly inspect the system and see that the Watcher is actually installed. You can only sort of side inspect that the BIOS is actually, intact. So here's how the watcher basically works. So it's sitting there in system management mode, and all it does is it sits there and it watches. It's extremely tiny because it doesn't like build in all the capability in the world. It just tries to find capability sitting somewhere in memory, right? So all it has to do is know how to scan memory. And if it scans memory, finds a magic signature, then it will execute as code whatever is after the magic signature. So some controller puts something into your memory somehow. There's many different ways you can use your imagination. They can send stuff over the network. You can open up a document. They can control your web page rendering, whatever. Somehow an attacker gets some memory set a particular way on your system. The watcher is already installed. It's always watching. It's always waiting. And it's continuing to scan memory, and it finds, bam, there's a magic signature. There's some code that I should execute now. And when it executes that code, it does whatever the attacker wanted it to do. So this is why we sort of say attackers can do anything. They can do every single type of attack that's possible later on the system, because this most privileged execution domain can just pull in arbitrary code and execute it for the attacker. So can do whatever. So in the comics, the Watcher is sworn never to interfere, but he's always interfering anyways. So the most famous thing is he tells the humans that the Devourer of Worlds is coming. So we wanted to make it clear that we just did the exploit from Windows, but the SMM agent is sitting there below the operating system, below the hypervisor. It sits there, it lives forever, it's persistent. So we just booted the system, the same Windows system, into Linux. And now we're going to show that the Watcher is still sitting around, waiting and watching, waiting for some payload to actually be installed into memory. And then if it finds it, it'll execute it. So this is just a simple thing. We have a little I/O application. It's going to cause a system management interrupt. It's going to wake up the Watcher. So we can either have the Watcher running all the time, or we can only have the Watcher run on demand. For simplicity, we're making the Watcher run on demand right here. So I have a little application. It's going to wake up the Watcher. And in this case, if I pass argument 8, it woke up the Watcher, and the Watcher didn't find any payload because we didn't put any payload into memory. So I do this I/O 8 a bunch of times. The Watcher is waking up, scanning all memory, and not finding anything. But if I do I/O 9, this application will now create a magic payload, just stick it in memory wherever, and then it'll wake up the Watcher will find it, and then it'll go actually execute the payload. So there you go. The Watcher is waiting, hiding, executing stuff. So the Watcher printed out, though I'm forbidden to interfere, maybe just this one time. And then the payload there, that's actually the assembly code that it found in memory. So all that assembly does is it just gets a address for a print function and passes the arguments into print. So the key point is payloads can do anything and everything, and if we had more time, we'd show all sorts of more fun stuff. So now we're going to go with our last thing, just 50-50 chance it works. In the comic books, ultimate nullifier, powerful weapon, most powerful weapon in the universe, can destroy the universe. Well, in BIOS world and with the breaking system world, or in the breaking systems world, we care about if you can corrupt the entry vector of the BIOS. If you corrupt the very first instruction that ever executes on the BIOS, there's no error handling at that point. There's no recovery from that. So if the first instruction is an error, there's nothing you can do about it. You can't boot the system. You can't boot from a boot CD and re-image the system, right? You're just dead in the water. The system will never, ever run again. So we're going to try this. We got like a 50-50 chance that it'll actually work. We're going to send in this payload through ping packets over the network. So we just want to make the point that, look, any way that the attacker can get stuff into memory. So this thing's not really listening or caring. It's just the ping packets show up in a memory buffer, and the Watcher, if it finds it, will go ahead and execute it. So so I'm going to manually configure that. You talk about what we're doing here.
So essentially, yeah, what we have with this particular proof of concept is that Xeno is manually causing the SMIs. There is a way to program the chipset to periodically generate SMIs so that we can have the Watcher running all the time. But in this case, one, it was we were kind of working on getting the Watcher done late into the evening last night, and it was hard to implement the periodic SMIs and make sure everything else was working. And just so you can see that we're manually initiating the Watcher through generating an SMI through this port I/O. But yeah, when we have the whole finished weaponized thing working, and it will be running on its own all in the background. So Xeno just set up the Mac to start pinging the system. We're going to cross our fingers and see if it finds the payload. There are some buffering issues, But finally, it reads the bytes coming in off the ICMP packet, which is just to brick the system. So you can see right there, it did actually just find these bytes it was looking for in the ICMP packet. And the system is actually bricked right now. Like if we try to reset, it'll just be dead because we've overwritten the reset vector with 0.
All right, so yeah, like you said, we saw the watcher printout. We didn't see any like payload print because all this payload does is it overwrites the very first instruction that the CPU ever executes. So we can show that like at this point, if I reboot the system, it'll just, never come up again. I powered it off, powered it on. There's no like magic like booting up kind of thing. And then just to show that a little further, we're going to show that this was just sort of a surgical 4-byte write at the reset instruction, and now you can no longer boot your system. So the reason we obviously care about this kind of thing is that if you have, oops, I just programmed it to overwrite what I was doing. Crap. Cancel. All right, I don't know if this is going to work now because I just overwrote maybe what I was doing, but let's try it anyways. Read it and then see what we can find.
Yeah, it's definitely bricked now.
Yeah, it's definitely bricked at this point. All right, recognize my thing.
So Zeno was basically pointing out that the idea here is that you want to have some agent listening in the background, and if hostilities break out with another country, that the enemy country could just send a bunch of packets to your systems and just like remotely break them once they have this agent installed by exploiting your firmware. So that was sort of the idea we had behind this proof of concept.
All right, so basically, like I said, so the reset vector on flash chips, the flash chip gets mapped to the highest memory address. FFFFF0 is where the CPU will always pull in the first instruction from FFFF0. And so if we go there, on this chip, it's 3FFFF0, then, I accidentally started overwriting it, but there you go. It won't break, it won't run anymore. This would have just been like 4 bytes of zeros in order to show it if I hadn't accidentally started rewriting it. All right, so we're over time, so we're just going to skip to our conclusion slide. All right, so the point is, So also, Copernicus, go read the slides. We have, you can actually detect this. We have a tool out there which checks the BIOS flash, finds out whether there's any backdoors installed into it. But basically, Copernicus, the King's Gambit, Queen's Gambit, this is part of a growing menagerie of many different attacks down at this level, and if you're not paying attention to these, you're going to get burned. So with that, we're done. No time for questions. We'll catch you in the outside.
Yeah, thank you very much. Any questions out in the hall? And enjoy the rest of the show.